All right, well, let's step through breadth first search on this particular graph. So we'll say that S is the start vertex, and the entire graph here is given by G. We're going to mark everything as not having been found yet, and I'm going to do that by just not marking anything. And then as things get found, like I do here on this step, I'll just check it off here. If you're notating this differently on the sheet of paper, that's perfectly reasonable, but it is worthwhile to go through this actual process at least once to see how it sort of plays out. We're going to have a visit queue, so I'll just call that queue, and I'll add things to it here. So that currently just has the start vertex on it. And then the first thing we do inside the while loop is pop out that start vertex and then loop over all of its edges. Well, these would be the two edges of the start vertex. So the other two vertices, A and B, have not been found, so we will mark them as found and add them to our queue. And you can see that it's hard to sort of see what's going on in our algorithm here just by what I've already written. So a lot of times what I will do is if I have an iterative algorithm, I'll just look at the looping variable, which in this case is going to be vFound. And we'll just say, okay, for this first iteration, vFound is equal to S. And then what does vOther take on? vOther, and I'll just abbreviate VO so I don't have to type out other every time. vOther first is going to be A, and then vOther next is going to be B. And that has resulted in me checking off A and B and putting both of them in the visit queue. Now, when I come back to the top of the while loop, after I've looped over all of S's vertices, edges, I'll pop off a vertex, which is going to be A this time. So we'll say vFound is equal to A, and we'll look at all edges connected to A, which are these two. If we're doing this alphabetically, like I've got down here, we're going to go to C first. So vOther is C. We check C off, and we add it to the queue. Now we have vOther is equal to S. And S has already been found, so there's nothing more that needs to be done. This if statement here is going to just be false, and we'll skip over it. Well, that's everything for that iteration. So in the next iteration, we have vFound is equal to B, which means we had to have popped it out of the queue. And it has 3 edges connected to it. So alphabetically, we would say vOther is equal to C. We don't have to do anything. C's already been found. vOther is equal to D. We'll add D to the queue and check it off. And then vOther is equal to S. Nothing to be done there either. Now if I come to the next column here, the next vFound is going to be C. So I'll pop it off the queue. And C is connected to A, nothing to do. B, nothing to do. D, nothing to do. But E, we do need to add to the queue. And then finally we pop off D. And it's, we could keep typing this out, but as you'll see, we've already found everything. So at this point, we could just say the order in which these vertices are visited are S first, A, B, C, D, and then E. All right, well, what's the running time of this algorithm? Let's start by answering this. What's the running time of this outer loop? Well, the outer loop is dependent upon the visit queue, and the things we're putting on the visit queue are the vertices, and each vertex can only be added to the queue once. So it's pretty reasonable to say that this outer loop is going to iterate big O of n times. Now, if you can't reach every vertex, it's not going to be exactly n, so I'll just put big O of n to denote it depends on the size of the number of vertices in the graph. All right, well, how about the inner loop? What is the running time of the inner loop? The inner loop's actually quite a bit trickier. What we might be tempted to do is to say it's big O of m because we're looping over the edges. However, that's a bit of a simplification because we don't loop over all edges every single iteration here. We're only looping over the edges of a specific vertex. So maybe an easier question to answer is, how many times do we consider each edge here? Well, we have to consider it once, for example, when we're going from a vertex. Let me just use a more generic vertex label here. When we're going from a vertex X to a vertex Y, well, V found here could be X, and then later in another different iteration it could be Y. So it turns out for each edge, like this XY edge, we'll only consider it twice, which means cumulatively, over the course of the entire algorithm, we do big O of M work for that inner loop. Not for a single iteration, so we're not going to multiply. We won't do that. But it's more of the outer loop is big O of N, plus we know that we're going to consider each edge at most twice. So it's more of an addition there, even though it's a nested for loop. So this is one of those unusual times where even though we have something nested, we're not going to have a multiplication of the two, because we're not considering all M edges for for all of the N vertices. So I'll denote that as big O of NS plus MS, where NS and MS are the nodes or vertices that are findable from the start vertex.